Alrighty, check 1, 2 is, I guess we'll go ahead and get started on this since the host seems to be busy doing other things. Well, my name is Brian Houghton, and we're going to do a presentation today on full pin switches. No, actually, we're going to do GPS guided recovery instead. And I guess to give you a little background on me, I actually have a very broad background in a lot of areas. Most of which is all God-given talent, and I'm incredibly humbled for that, and also very thankful to be invited to come share some of that with you people today. They usually don't let me out a lot, so. But GPS guided recovery is a topic that can have a lot of different facets to it, basically. And the first question is what is GPS? Basically what it is a national resource. Probably you guys all know what it is, but it's a national resource where we have spent billions of our tax dollars to put satellites up into space for global positioning. That's what the GPS stands for, Global Positioning System. And with that system, there's about 31 or 32 satellites up in space, depends how many are working at any particular time. And they usually use about 24 of them at a time. And these satellites are basically flying at 20,000 kilometers in space, about 14,000 meters a second. And they are not in geosynchronous orbit. A lot of people sometimes think they are, but they're circling the Earth about every couple days or something like that. And the way the system works is that each satellite sends out a Presidio code that's unique to itself. And then in order to use this national resource, basically what you have to do is like when you go to Yellowstone or something like that, you have to buy a parks pass. But in this case, you just buy a little GPS chip and anybody in the public can use it. And those chips, they also generate the same codes that the satellites send out. And then they do a time of flight calculation where they can measure the phase shift between satellites and the receiver itself and get a distance to the satellite. If you do just one satellite, you can find your spot anywhere on a circle, which is the circle of travel that the satellite's traveling on. And so in order to get an exact position on the surface of the Earth, you basically need like 3, but 4 is better, 5 is better than that. Typically there's about 8 or 9 satellites in view any place you are, which would give you the best resolution and accuracy. They are coming out with a new GPS system. I think they're launching satellites for it already. It should be up and running here in a few years. And I hope they make it backwards compatible, or otherwise it'd be like a Microsoft thing where everybody's got to upgrade, and we don't want that. So the question is, if we know a position on the Earth, why would we be interested in using that in flying model rockets? Does anybody have any ideas? Yes, sir. That's a good one, yeah, definitely.
Find your rocket.
Find your rocket, that's almost the same as not losing it.
We're lazy, we don't want to walk.
There you go, that's a good one. Those are all, yeah,
You
Steve.
can fly the rocket out to a position in space and then have it drift back towards you.
That's a good one too. Yeah, there's a lot of reasons people might want to do this. I guess I decided to do it because it sounded fun. So that's some of the reasons why we might want to use this in a rocket system. Now, when you talk about basically what we're talking about, which is landing something in a particular spot on the Earth, there's a couple different systems that we can use. This probably is not certainly inclusive of everything, but basically we can divide the systems we can use into 2 different categories. One of them is a rigid system, and one of them is a flexible system. Now, a rigid system might be something like that Joe Menard's working on, where he's doing vector thrust type stuff on a rigid body. And we just saw a demonstration of how that works in real life last night. Anybody see that?
Yes.
Excellent. Another rigid system might be something like a helicopter type device thing, whereby we have something spinning or 2 things spinning or whatever, and we can kind of guide it down and land it wherever we want. Maybe another type of rigid system might be a glider, where we can, pop out some wings and glide it around and have it land in a particular area or spot or whatever. And what's interesting about the first two that we talked about, which would be vector thrust or a helicopter type, is they have the ability to control coming straight down. Whereas a glider, for example, it has to have forward momentum. So that's just some subtleties in, there's, like I say, a million different ways you could probably do this. And then if we decide to do one of these systems with rigid parts, the issue with it is that it's hard to put in rockets, perhaps. It takes crazy parts that we have to build, or they don't quite fit right, or we have to come up with these mechanisms to pop wings and helicopter blades out and things like that. So what's actually more conducive to rockets that everybody's already built is they can do something more like a flexible system. And if we look at a basic flexible system, we have a parachute. And instead of having a bunch of rigid pieces and parts, we kind of just have some cloth and string. Now this right here is a basic ballistic chute. And I'm sure you all pretty much know how these drift away and work and get stuck in the trees and things like that. But what's interesting about this is it's kind of a very first point. And what I'm going to do today is I'm going to just give you guys a lot of advantages and disadvantages to a lot of different systems. We've already talked about the rigid systems. They're kind of hard to put in existing rockets. They are actually easier in a way, which we'll get into more. But basically what we have is a mass that we're trying to lower at some slow velocity so we don't break the rigid parts on our rocket. And we're going through some medium, which is usually air. And how many people have seen, like when your parachute's coming down, it'll be coming down really nice and all of a sudden it'll go this way. And then it'll come down for a while and then it'll go that way. It's kind of crazy sometimes what the air currents do. But you do have to consider them because since we're talking about falling through them, they are going to affect whether you have a rigid device or a flexible device, or you could even have a device probably looks like a 32 Ford fender and it's going to be affected by the air. But this is an interesting type of chute. You can actually make this, when you're talking about flexible systems, in order to make it go someplace that you want to instead of just being at the whims of the wind, you have to have some forward momentum. And in flexible systems, we call that basically traction. How much traction does a device have? Which means how fast does it come down versus how fast does it go forward. So it's similar to a glider. It's not going to come down, obviously, like a vector thrust system because it cannot come straight down and still be able to do things unless it's just one of these. So in order to make this into something we can control, usually, you might be seeing pictures of them, they'll come in the backs of them and they'll cut holes into them, slots and all this other stuff. And then by pulling on different lines, you can get it to go this way or that way. Now the main advantage of this type of system is there's only one foil, which means it's made out of one sheet of fabric. And it's a really simple form. Another advantage of this type system is the riser lines in here. There's typically a minimum of them. Although when you start adding steering to it, you have to start adding more lines. Now the disadvantages of this type of system is that it has low forward traction. It doesn't go very fast forward. And it has a tendency to want to spin because it has a low moment of inertia. So that's kind of the basic first starting stepping point. Now if we want something better than that, the next simplest one would probably be one of these guys, which is a parawing. Now this happens to be a single keel parawing. The keel is this part right through here, and there's only one of them, so it's a single keel parawing. What's good about it is it does do have a low riser line count, and it's also only got one foil. And it does have fair traction, better traction than just, a ballistic chute with some holes cut in the back. The disadvantage of this is it also doesn't really have all that great of directional stability because of the single keel. Also, it only has, it's got good traction, but it's not the best in the world. So that's kind of the advantages and disadvantage of a single keel parawing. And then what we can do, another kind of interesting thing about this type of parallel here is that the line lengths, these riser line lengths, they're all longer than the keel. And that's an important point because the less lines we have and the less length we have, the less apt we are to get things twisted and tangled. And so if we look at maybe one that's a little better than this, that would be a dual keel parallel wing, also known as a Rigaldo chute. Now the advantages of this, that you can see there's one keel right there, and there's one keel right there, and then it has a wing on each side. Now the advantages of this, it has one foil. It's still got a moderate riser line count. It's got fairly decent traction. And it's got good directional stability because it has two keels in it, just like a double keel boat will have more directional stability than a single keel boat. Now the disadvantage of this is it's slightly more complex than any of the other ones we've been looking at, obviously, because we're kind of adding to them here. And another interesting advantage to this is all the riser line lengths are shorter than the keel length. And if you extrapolate that out, you can add any n number of keels that you want. And the odd numbers will have longer length lines, and the even numbers will have shorter length lines, until they converge together at one that basically has a lot of keels, which would be the next one, which would be like an air ram parafoil. Okay, they have a lot of riser lines, so usually they cut them short and start putting them up into here. And you can, they actually call them cells, but you can kind of look at the cells as they transformed into keels. This is a very high performance chute. Has high traction ratios. You can actually even get some stunt chutes that are higher than that. Now, the disadvantage of this type of chute is it is high performance, which means it's going to be harder to control. It's going to be faster. And that's one of the problems that we run into in rocketry because we're limited by the sensors that we can afford. It has a very high riser line count, and also they're usually double foiled, which means they have a top foil on the top and a bottom foil on the bottom, and they fill up with air and make like a wing shape. If you look at the cross section of this right here, you can see a wing. And that's what gives us all the advantages, but another disadvantage of that is now it's twice as heavy and twice as big and twice as hard to fold up, and so maybe not so desirable. So those are basically, like I say, the how you can go from a round chute to a really high performance chute in something that will have traction, which is what you need if you want to land something at some point. And then, once we figure out what kind of chute we need to find some kind of control system. And I hope I don't bore you all with this, but I did a lot of work in modern control theory and control of spacecraft and highly maneuverable aircraft. And that was a long time ago. I don't do it anymore. It's too hard. It hurts my brain. But what ends up happening is if we go through the basic, and I'm just going to give you the basics, but if we go through the basics, the easiest type of controller that there is in the whole world is called the bang-bang controller. There's a lot of, in this building right here, they're called the light switch. On-off, that's a bang-bang controller. Well, the advantage to them is they're time optimal. That's a time optimal device. And then you guys have probably heard of these other ones. If you get to classical controllers, there are PIDs and PDs and lead lags, and those are just mathematical concepts, but there are ways to get better control than, for example, a bang-bang controller. And then just as we did with the chutes, we're going to do the same with the controllers. A slightly better one might be a fuzzy controller. Those are typically rule-based controllers. And then maybe a little harder one is, you can add some nonlinear math things in there and see what happens. And if you want some really kind of interesting ones, they don't work in all applications, but you can get them to do a lot of things for you. They work really well for recognition of patterns and stuff like that, for example. But it would be an adaptive controller or maybe an artificial intelligent controller. AI is starting to become a big control thing. And then we have an expert control system. It tends to work really, really well on systems that aren't very fast. Does anybody know what an expert controller is? Exactly. A human operator is an expert controller. They do the best on many things. For example, an overhead crane, gantry crane, with a swinging mass underneath of it, they will outperform any of these other type of controllers until you start getting into these down here, hands down. That's because we're pretty good at what we do. So those are just basically from the simplest type of controller you can have, all the way to one that is really good, and everything in between. There are a few other categories, but that's basically it. Now that we know what all these controller types are, we can apply them in different methods to make something happen. And since we're talking about going to a position on the Earth somewhere, these would be positioning kind of methods. And the first one would be dead reckoning, where we just go out in our boat and we get our compass and our sextant and we say we're going to go that way till we hit land. And if we get everything right, we'll end up somewhere over there and hopefully run into land. And then the next kind of simpler one, or harder one, however you look at it, is a direct line where we know something on that end and we can track to it. We can still use our compasses and sextants and everything else, but we know exactly which direction we're supposed to be going, so we're gonna, because there might be a lighthouse over there or something that we're gonna try to track to. And then we can do things like zigzag controllers and maybe advanced and predictive type path network type systems if we were ambitious. So this is basically kind of all the possible choices that we have for doing some kind of guided control, or at least categories. I mean, there's definitely subcategories and some other odd ones that would just be a waste of time mentioning here. And so if we look at a basic control system, I know some people have tried doing guided controls before by just doing GPS. So what we have here is we have a desired location we want to go to, and we have a GPS chip, one of those ones tied into our satellite network, and it's telling us our current position. And we can do vector math right here and figure out which way to go to get to our desired position. This can work if we had a fat stack of Franklins and the government guys would sell us the GPS chips they use in the front of their munitions. But most commercial GPS chips like that we have access to, they have fairly slow update rates, maybe a second or something like that. Their accuracy is, plus or minus 10 feet, 20 feet, something like that. And because of the cost of these chips, that's kind of what we're stuck with. Well, a lot of those chutes we were talking about, especially if you get to say the last half of them, they have the capability to turn 300, 400 degrees a second. So if somebody wants to track with just GPS that's updating at once a second, that means a chute could turn all the way around and then past that before you get another position update. And that's not really conducive to making something do what you want. So probably a better way to deal with it would be to add an inertial controller to it. And so you can take like gyroscopes and accelerometers and some magnetometers and make an inertial measurement unit. Now there's a couple different ways you may have heard people making this. One, you can do it with quatrains, which is just some fancy math. And it has some advantages. Another way you can do this is you can do it with rotation matrix and Kalman filters. And it has some advantages and disadvantages. I kind of like Kalman filters, especially for if you want to really, it actually has less multiply and divide operations than doing it with quatrains. And you also get, if you look at the transfer functions for Kalman filters, they're actually low pass and band pass filters, which means you get some filtering kind of inherently in your sensor fusion algorithms. So then we're actually going to try to have to use this because we can make this fast. And we're going to have to try to use it to control which direction we're going. And so out of a typical IMU, like this, you'll get a pitch rate, a roll rate, and a yaw angle. And the angles, rates and angles usually. So what we can do is we can take the yaw, which is the direction it's going, and every once in a while, once a second, compare it to this guy that's telling us really slowly which direction it's going. And we will have enough speed through this system then that we can maintain control of whatever we're trying to do here. So this is probably a much better way to do it. Like I say, the sensors we have to use, we actually have to use crappy sensors up here. We use MEM sensors, they're called. They have a lot of cross-channel coupling. They're relatively slow, especially the mag sensors. The whole key to your control is you have to have a control that is faster than what your chute can turn at. If you don't, you'll never catch up. So that's why we try to get things fast, and that's why GPS only doesn't really cut the mustard very well. So anyways, then we send it through a controller and send it out to our servo. One thing we can do, if you guys are interested in advanced stuff, is we can feed forward the roll, and if we feed forward through a nonlinear function, that gives us damping in the roll direction. And we can do that because if we tell the chute to turn, it's going to automatically tip and roll. So that means this axis will be in phase, and so if we feed it forward, it will damp for us. And if we talk a little bit about a chute, what we put into it is we put in a command with the servo by pulling on the little Army guys' lines or whatever. And we are putting in, commanding a rate. We want it to turn at some rate. And so what the chute does then is it starts to turn. And what we really want is we want a position. We want it to go to a spot in a direction. And so if we take the turn rate and we integrate it, kind of right here, we get, this is an integrator for those of us that do it that way. If we integrate the turn rate, we'll get the turn angle, which is what we want. So that's all kind of this stuff means down here. And like I say, this is a model of a parachute right here. I don't know if you're really interested in it, but I have this thing on here called HOT. And what does that mean? It means higher order terms. This first part here is just a real simple integrator. But in real life, you get oscillations and bending moments and everything else. And because of these higher order terms, that's actually how come rigid systems are much easier to control than flexible systems. Because in a rigid system, they tend to be more damped, just because you have to bend metal or whatever. Whereas with some string and some cloth, you can end up with some, lots of higher order terms that you have to be able to handle. And then we just basically take that and come up with one of those controllers from off that other page, the last page, and we stick it in here, and the whole thing hopefully theoretically should work. I just put this on here. This shows whenever we do a digital system, we have to remember to transform it into the digital domain. So this is a bilinear Z transform, and it's got the sampling rate in it. And that's important because it sets your gains in your controller. If you can you have to sample. I think if any of you have gone to Joe Bernard's speeches, he talks a little bit about sampling. You have to sample. I usually try to sample as fast as I can and lower the gains as opposed to sampling slower. But anyways, this would be a typical control system for if you wanted to really try to do this. Okay? Now you'll notice on that last slide we didn't have anything going to the pitch. Although we could if we wanted to, because we already got the pitch numbers. But we have an interesting thing when we hook this to a rocket, and that is, if you remember the very first slide, we had a ballistic chute with a mass under it that we were trying to lower to the ground through some medium. It's almost like this, but not quite. Because what we do, if we decide to stick a controller in here, that's going to be where the mass used to be. Now all this stuff hanging down here, that wasn't in there before. But what this does is by hanging a rocket below a parachute, it actually gives you pitch feed forward also, just like roll feed forward does, so it'll tend to damp it, which is a desirable feature. So for example, if this thing turned into the wind, the airframe would fly back farther, which would pull the nose down, which would give it more bite into the wind. So it's like we get free pitch control. You could add real pitch control and make it better, but I like free. So, but then, as far as hooking a rocket to it, there's only one key requirement to this, is the system has to be separable. So right here at the bottom of these guys, we have to put in a really good swivel, right there. If you don't have a swivel, then if these fins are spinning and twisting, all it's going to do is twist the whole thing up. But by putting in a really good ball bearing swivel in there and making sure you don't have dirt in it, then basically the top half and the bottom half are totally separate from each other, and all the bottom half does then is add pitch to it by swinging back and forth. Now there's two ways you can do it. You can either hook your parachute on like most people do, say a third of the way down the lines. These lines aren't to scale. I usually like when I fly rockets because I don't like breaking them. I'll make this line here like 4 or 5 times the length of the rocket, and then maybe a fifth in there or something like that. But if you're going to try to do some kind of steerable GPS guided thing, you kind of want some mass right here. So I just move everything around and move the nose cone up and use it for a mass. Try to get the nose cone, right close to the bottom of this thing, and then make this line really long. And you can do it one of 2 ways. You can do it like typically where you connect this line, say, in the middle here. Or you can flip the 2 over and connect the nose cone and then the chute on the top of that. Either one works. If you look at all the numbers and simulations and everything, I actually think this one probably might work better, although right now I'm kind of looking at that one. But what's important to remember is you need your nose cone up kind of close, and you want that way, like most people usually do their rockets. So that's the difference between doing a one-tail. You have to be careful if you are going to do a two-tail one, which would be this one. This is one tail. Everything's on one cord. This is 2 tails. If you have too much length in your cord right here, this piece and that piece will get in a flat spin, and they'll be spinning. And the chute won't be able to compensate for it because they are driving masses and they weigh way more than the chute does, and they're going to do what they want to do. So that's kind of one of the tricks to making these work. So that's kind of how that goes, how you hook it to a rocket. Now if you really wanted to fly one of these, since you're going to have to eject more things than just a parachute, there's always the ground test thing. And the effect of winds. The wind, it's hard to say what the wind's going to do because you don't know which way the wind's going, that way or that way or whatever. But basically, if you pick the simplest control for these guys, which would be just a direct line controller, typically will happen in the wind is that when you fly your rocket, it's going to track upwind, okay? And then let's say the chute comes out, then the direct line would be downwind, back towards, wherever it launched from. So it will fly at high speed then, because the speed of the system will be the wind speed plus the forward speed of the chute, until it crosses over that point, and then it will turn and start trying to fly back upwind to get back to the point again. If there's no wind, it'll just keep flying back and forth over the point. But if there is a wind, and it gets downwind, the system does, then one of 3 things can happen. It can have enough forward speed, let's say the wind's blowing 10 miles an hour and your rocket can come down and go forward at 5 miles an hour. That means it's going to go backwards at 5 miles an hour, the difference in the speeds. Or if they're both equal, then it will drop straight down. If the system can fly forward faster than the wind, then it will begin to approach you. So that's kind of what the wind's going to do. And in this type of system, it's always going to try to get downwind because that is the least energy state for everything. So that's kind of what the winds will do to it. Typically, you can get these to fly if you don't use a high-performance chute, 5, 6, 7 miles an hour, something like that. And then the deployment altitude. The only reason I put that there is because I think if anybody tried one of these and they shot it up into the jet stream and popped it out up there, it might not work so well. And then since they are steerable systems, you have to trim them so that they fly straight. They take, the line lengths and everything have to be right and all that, and occasionally you get strange pulls in fabrics and stuff, so they're not, maybe when they make the fabric that you make this thing out of, it might not be exactly even, so they'll slightly turn one way or the other. And for the best results, it's better if you can get them, when there's no command input to them to go straight, they just go straight. That's the desirable way to do it. So then, what we did with all these is we took all the systems, control methods, sensor methods, and we did a cost functions on them all and reduced them down to get the one that's, the smallest, the cheapest, the most optimal for whatever cost it is. And what we come up with is the double keel regalia. And this is a picture of one flying right here. And I happen to have one right here. Let's see if we can get it to pop open. And I better come off here so I don't fall off. But you can see it. It's kind of hard to, when you see the sides rippling in, that's because I'm actually pulling it. It's not truly flying itself, but you can kind of see how that it could possibly work to fly something back to where you are. And they actually do work. Now, I did a lot of development on this, but also Tim Van Milligan from Apogee Components, he's done a fantastic job of sourcing some of the components, cost reducing it, getting it so that perhaps we can get it into a kit form, just working on a bunch of aspects of it. And so, since I bored you all with the control theory part, I'm going to turn it over to Tim now, and he can let us all know, you know, how the actual kit formation and progress is going on that end.
Thank you, Brian. As you can tell, with all the math that's involved, and what he's done so far is just incredible. And maybe I'll try to get into our personal story here too. This is a video, so go ahead and start it playing. This was November of 2017. We were out with Steve Bennett, another club member from Cos Rocks. This is how we tested the device. Brian's holding the controller in his hand, and we have a drone that just yanked it up into the air. And this was like maybe the third time that I had seen it, and this was the first time that Brian got it working. So Steve would haul it up about 300 feet, and to release it, there was just an L hook on the bottom of the drone with a little hook that went over that, and you'd go forward and then kind of try to pitch up, and then it would release the parachute. And at this point, Brian was flying, so there's a release, it opens, and Brian is flying it with remote control with a joystick. And so I was telling him, okay, turn right, turn left, and so I think he's making a right turn there, and then he's going to come around and do a left turn. And this was the key, is having control of it. Because if you don't have control of it, if you don't have control of a gliding parachute, it's going to go in the path of least resistance, which is downwind. And you know, and they are very efficient. I don't know if anybody saw my latest newsletter, but David Flanagan wrote an article on efficiencies of gliding parachutes, and if you're comparing CD ratio, this parachute has it's about 6 times more efficient. So that means it's going to go 6 times as far, drifting with the wind. So this is another video. This one we did in January up in Denver, so there was snow on the ground. And this is a GPS flight. So by this time, Brian has gotten the GPS controller to work, so we were hauling it up into the air. If you hit the volume button, I think there might be some volume. It's kind of on the top right. I don't know, you probably can't hear it, but it's basically the sound of a drone. And somebody in the parking lot behind us going beep, 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 beep. So again, we haul it up in the air. And this is the way, if you want to trim a glider, you got to get it in the air. And the drone is the best and cheapest way. So I recommended to Brian to go out and get a drone, and he did. And he's been flying them hundreds and hundreds of times. And you can tell when they work because they always come towards you. And this one made a turn. It came over what Brian said, if it comes over the landing spot, it wants to circle back around and keep
Oh, that's
tracking.
cool.
So there it
Nice
is,
turn
it
there.
circled around, and it landed, that's where it took off of that box right there. So that's kind of cool. You can go to the next one. Go ahead and do this one too. This is another video. This one where it really, where it landed, it landed actually behind us. So
What
it just
happened?
went up and it came around, went over the target point, and then just kept going. And then it ran out of ground, it ran out of airspace before it had time to turn back around. But the way the system works is where you turn it on is where it wants to come home to. So if you turn it on the launch pad, it'll try to fly to the launch pad. But because it is a GPS system, there's usually, when you turn on a tracking device, you have to wait for it to get GPS locked. And
Still
how long
150
can
feet
that,
away?
It could be anywhere from 2 minutes to 5 minutes to get, lock on the number of satellites. So typically what we do when we launch it is we do it at our car, which is not really the best thing to do, because in our safety rules say you don't want to land, here's Steve nodding his head, you don't want to land in the parking lot where the cars are. So what I do now is I go out, I don't go to the launch pad because I don't want to hog the range, because what happens is when you're launching a rocket, and if there's a rocket right overhead, the launch conductor is not going to launch the next one until the first one clears out of the way, so you're hogging the air. So I go out about 100 feet down range, and I turn on there, and then go to the launch pad, launch the rocket, and it tries to fly to that place. So that's my recommendation on it. So as we were saying before, why have a system like this? And the first person that put their hand up was said, I'm lazy. Well, I'm lazy too. You can join my club. And it's also really cool. As you can see, it's when they're gliding, it's a lot different than a regular parachute coming down, because it's actually doing something. And again, I don't want to spend my day hiking. I want to fly as many rockets as I can during the day. Go ahead, Brian. And this is kind of redundant of what Brian was talking about earlier. I've been working on this idea for a number of years. I flew my first Rogello glider or parachute in 1992, and I got hooked on them, and I wrote articles in my newsletter. And over the years since then, I've been trying to find people to make this for me, because it involves a lot of math, and I'd rather have somebody else do it than me. And I don't know anything about control theory, so I'm not the one to do it. So I asked Brian. He came into my office one day, and I said, "Hey, Brian, what you ought to do if you got the time is to do this." And so we started with the parachute. You could go with rigid gliders and helicopters. It's possible to turn a helicopter into a recovery device. Roton was trying to do that a long time ago. But the easiest is the parachute. It's easy to stow on the rocket and can be controlled, and it offers redundancy for safety. If the controller doesn't work, it's still a parachute, so it will still come down safely, which is a nice feature. Okay, next. And as Brian was talking about, you can start with a regular ballistic chute and cut holes in the back and use that as control. The Army does this a lot, but you can't really penetrate into the wind, which is its downside. Go ahead, next. Rogello, again, it's the lowest weight parachute. Remember, these are 6 times more efficient as a ballistic parachute, so you can make your parachute a lot smaller. So when you are putting one of these parachutes into a rocket, it's going to look really small, but it will still come down really slow. So you get an advantage there. You're lessening the weight of the rocket by putting a small parachute into it. And it's got pretty good wind penetration, and it's a lot less expensive than the Ram air parachute, because you don't have to have 2 pieces of fabric on top of each other with panels in the middle. So it's a lot cheaper to make. But it still requires trimming. If you've flown gliders, if you're going to fly a glider, you got to trim it. So Next. So this is what we saw earlier, the components. At the top, we have the twin keel para wing. Below that is the line separator to keep all the lines apart, and so you have some a moment arm to pull on those lines. Then you have the controller, and then below it is your payload. In this case, is the nose cone and the tubes. Go ahead, next. Again, here's the line separator. This is, I think, Brian came up with the line separator. When I was trying to fly him in 1992, I didn't have the line separator on my rockets, and I could never get him to work the way I wanted to. But that line separator is, I think, one of the crucial components, and it's such a simple little piece of square in there. Go ahead, next. This is the controller that Brian was holding up. It's hard to see, so we blew it up here. There's 4 sets of lines coming out of the controller. There's 2 static lines, and then the 2 steering lines. The steering lines are controlled by the servo. Right there, yeah. In front of that is the battery. On the back side is the GPS board, the real controller. And then there's a board on top, which is the manual control. So this system, the way we have it set up right now, is you can either let the GPS control it, or you can take over manually. And the advantage of manually, like Brian was saying, is the expert control system, where you can fine tune it to make it come down to where you want it. Now, this is kind of an optional thing. For me personally, when I'm watching the rocket, I don't want to be steering it. For me, I like the GPS, just let it come home. Brian likes the manual method. And then there's the quick link and the swivel on the end, like you were saying, it has to have that swivel on there. Most of the load is carried by the fixed lines, and on this model right here, these are the fixed lines, so almost all the weight of the rocket is on that. There's 26 lines on this one, 26 lines, so 3 of them are steering lines, or 3 on each side, so 6 of them, so 20 lines carry the weight, and then the other 6 are for steering. Go to the next one. This is a more close-up view. You can see the servo there pulling on the lines. This is the bottom side. There's the GPS chip. The bottom of the servo is there on the right. We also have it in a clear tube. Brian put some LEDs on there that give you the status of it. And they're a lot easier to see when there's a clear tube, and that's why we have the clear tube on there. And then there's pointing to the manual controller. Go to the next one. This is the controller, the handheld controller. As you can see, it's just got a dial on it, so you can only go to the left or the right. You can't do anything else. It's got an on-off switch on the left side, and then on the right side is the switch for letting it go to GPS or flipping it down into manual mode. So it's really easy to use. So on the left side here is the GPS mode. The switch is in the upper position, so it's in GPS. It's with the little board here that for the manual mode. It also has a transmitter on it, so it's transmitting its position. It's kind of like a tracker, so it'll tell you the longitude and latitude of the rocket in the air. That's not your position on the ground, that's the rocket's position in the air. And it will also give you a distance to the pad that it's trying to fly towards. And in the manual mode, which is on the right side, it will tell you how far over you've got it as a percentage of full stop. So at this point here, it's like 30.7%. Okay, so this is more flight testing. This is how we did it. Like we said before, either with the drone with just the simple L-line, or Brian built a special rig with a servo on it that would release it. It's a little bit more accurate, and you don't. What we found is when we swung the the glider out, sometimes it would do funky things with the downwash and of the drone. So just dropping it straight has its advantages. Go to the next one. So you're probably wondering, is this a product? And that is our goal. We started this in the summer of 2017. As I was saying, Brian showed up in my office one day and he wanted to sell me a baffle system for a rocket. And it was really cool. But I said, Brian, if you really want to do something, do this GPS thing, because baffles, you're not going to make a lot of money doing baffle, but if you do this, this has the potential to change things. But it was not an easy product to develop, and so it has taken a lot longer than any of the other products we decided to do. Our current position right now is the controller is done. We've got the servos, we know where we can get them from the supplier. The eBay itself is pretty much done. It's a simple eBay. The only thing that's really different about it is the sled itself is fiberglass. So all the loads is through the fiberglass sled, so it can't break. Well, I can't say it can't break, but it would be very hard to break. Okay, the next one. The challenges we've had so far is everything is custom, and some of the parts were hard to source. Right now, our current problem is getting parachutes made. This is a glider, and it has to be trimmed perfectly, like Brian was saying. It has to be trimmed so it comes in straight, because otherwise it's very hard to control. The quality on the parachute has to be significantly better than any other parachute that I've ever had made. And I've had some really good ones made, as you know. Apogee sells some really nice ones. But the order of magnitude has to be perfect, because if we're going to send these out to customers, they want it to work the first time. And so that's what we're working right now, is getting the parachutes made. We've got a supplier that we think that can make our quality. Now we're waiting on final prototypes, and then if those work, then we'll go into production on it. Like I said, this is a glider. It has to have high quality, and it also has to be trimmed, and a lot of that trimming is done during the manufacturing of the parachute itself. The other challenge is this is a parachute, and you know from experience that parachutes can have problems. It's got a lot more lines on it than other parachutes, so it can tangle. But the nice thing about the Rogallo wing is it opens very fast. So it opens so fast that hopefully it'll untangle itself pretty quickly. But it can also get tangled inside the rocket. So now we have an extra mass inside the rocket. So you have your nose cone up here. Then you have the controller, and then you have the parachute down here, and then you have recovery wadding down below that. Now you're probably thinking, wouldn't it be better to put this on top? Well, now you've got your lines crossed, and you get more potential to tangle your lines. So I've done it. This is one of the challenges that we've had. And as Brian was saying, these sensors have to be very fast. During his development, he's been updating the sensors and updating the software to handle all that stuff, plus the GPS math. I don't understand it like he does. It's pretty cool. Go ahead. So yeah, what we're still left to do is try to get quality chutes built, and we still have to write the operations manual, how to use it, how to make sure that when you use it as a customer, you can get high rates of success right from the get-go without having a learning curve like we've had to go through. And see if there's anything next. Okay, so you're saying, so you've seen it come down on a drone. Does it work in a rocket? So we got two rocket videos here. The first one is that white rocket in the middle. This is one of Brian's rockets. Is this Breaking Bad?
Where's that range?
This is at Pueblo, which is where we had Narum last year.
How heavy a rocket or how big a rocket are you designing?
This one right here is a BT-80 size rocket, probably about that tall. The controller itself is a BT-70, so
What fell off?
I don't think anything fell off.
Oh,
That's the wadding, yeah.
So the smallest this will fit into is a BT-80. But we've also flown it in 4-inch rockets, the same thing. And for me, Brian and I were having this discussion this morning. He says that it's easier to get it out of a BT-80. I say it's easier to get it out of a 4-inch too.
How heavy is the rocket you're flying?
What's that?
How heavy?
Probably, it was a thin wall tube, right? So it was a standard BT-80. Yeah. Well, you were flying it on an F engine, right?
Yeah.
Yeah. So that landed about 50 feet from the launch pad. This next one is this is a 2.6 inch high power rocket. You were flying it on a G motor, I think it was.
Yeah, it's a G75. It's
G75. This one's a little bit longer because it goes a lot higher.
What kind of wind speed did you have?
This particular day, the wind wasn't bad. It was about maybe 5 or 6 miles an hour. And so for the next few seconds, I'm trying to find it in the air. So that it's not there on the top right-hand corner. It's more towards the left.
Does that GPS tell you your altitude then?
No, it just tells you its position. I'll find it eventually. There it is. You see it's really high. And for the next, probably the next minute and a half, we'll watch it come down. This chute, this chute, probably, right? This is a 26-inch chute. This is the smaller or the medium?
I don't know.
I think this might be the medium size. We're planning on 3 size parachutes for rockets. The largest one is 32 inches keel length, which is kind of weird because if you think keel length is from the tip of the nose to the back, but it's actually, is an imaginary point out here in front of the nose. And it's from the back edge to that position of the nose is the 32 inches. You see it's fighting the wind here. It's wiggling around. You got all the mass wiggling around.
Is this under GPS control or manual?
This was GPS.
It was pretty windy that day,
And can
too.
you switch this tank? Can you switch it in midair?
Yes. So you could, if it gets close to the ground and it was going towards somebody's car, you could flip it into manual mode, turn it to the right. Brian, if it's going towards a tree, turn it away from the tree.
Does the system require the remote?
No, without the optional backboard, it's just GPS. So where you turn it on is where it's going to land. If you want the manual control and the information on its position, then you would need to get the optional manual board.
Looks like it's varying pretty quickly. Is that because of the mass swinging, or is it that rapid?
It's from the wind.
The wind, yeah, the wind's whipping it around.
What's it do when it gets, if it's really high and it's already over the position it's shooting for, what does it do?
Okay, I'll turn it back to Brian.
We have some data graphs that will explain that to you.
Yeah.
Alrighty. Basically, there's a lot of data we get off of it. Some of it I can't show you because it'll be too confusing. So what I have a couple graphs here of is the direction that it's flying and the distance to where it thinks it's supposed to get to. So here you can see what happened, and the blue line is the distance. So we started here close to 0 feet away, and we launched the rocket and it went up, and it didn't really go hugely far away, but it, 175 feet, maybe something like that. And so the ejection would have happened right here. And then what it did is it turned and started heading in this angle. You can also read this axis as angles here. And it started flying, and if you look at the rate of change of this is how fast it's flying actually, and that's a really steep line right there. So that means it's going downwind right now. The rocket flew upwind, it's going really fast downwind, and it got to within about, I don't know, 20 feet of where it was supposed to, and then it's kept going at a higher rate downwind. It's still flying downwind. And then when it got right here, somewhere you'll notice that here it was trying to fly that way, this angle basically, and then when it went past it, and now it's got to turn and fly at this angle, which is 90 degrees or something. So then it's flying back upwind, and you'll notice this line's not quite as steep as some of these other ones, but it's flying back upwind, and then it crosses over the target distance again. We get really close to it. So then it has to flip direction, so it says, oh, I went too far, now I gotta go back the other way. And then it kind of got a little, the wind started to come from the side, so that's how come you can see it. It's actually tracking at an angle trying to get downwind, which is why you see this downslope right here. While the distance is increasing really slowly. And then right here, it got hit by a big gust of wind, so it is actually facing the right direction. See, it is not turning, it is facing towards us, which is the way you always want it. But it's getting blown away. And it got blown away for about, I don't know, 10 seconds. This is seconds down here. It got blown away and then it stopped getting blown away and then it landed right there, about 400 feet away. As high as this rocket went, it probably would have ended up well over 1,000 feet away if you didn't kind of do some crazy back and forth things here. And then we actually have this graph, which is in a higher wind condition. This is probably over 10 miles an hour. And I have to apologize because I totally lost the data on the front part of it here. But when it launched from here and it probably went 300-400 feet away. And then it came flying back downwind. You can see it here. Well, you can't because the graph's missing. But it came flying back downwind and flew over where we were. And then it's still flying downwind, but this area here where the red takes a big dramatic change is when it spun around and started coming back upwind. And you can see how fast it's flying here and how fast it's flying from there to there. It's pretty fast. But then once it gets turned, which is right here at this point, then now it is flying backwards away from us, but it is still facing us because the wind is just overpowering it. And it got almost 1,000 feet away, but then I don't know exactly what happened. Either the wind died down or it got down lower below a layer of wind or something. But then it started actually, instead of continuing to fly backwards away, it started holding that position and dropping straight down. And then ever so slowly coming back towards us until it landed right here. So that's the kind of performance you can see. If you don't have any wind at all, it'll be like that last slide, and you'll just see it back and forth right above you. Back and forth, back and forth. And it'll typically, one of the issues with this is that the GPS, not only is it slow and only updates once a second, but it has lag in it, okay? So that means the actual position that the chute is at is not what the GPS is telling you. The chute is in front of where you're getting a reported position. All GPSs do that, especially, like I said, on the kind that we can afford. So that's how come if it flies over your head, it might fly out 100, 200 feet past you before the GPS actually picks it up and it'll turn and come back towards you again. Just depends on the wind and everything else. We actually have hysteresis in it. So if there is no wind, because you can't do control on a singular point in a way. I mean, if you have one point on the ground and it gets above that, what happens then? I mean, does it go in ever-ending tight concentric circles and come straight down right there? So what we've built into it is about 50 feet or so of hysteresis. So once it gets to where it's supposed to be, it flies 50 feet at least past it before it tries to turn and come back. And ad on infinitum doing that. Like I say, otherwise it's a kind of an undetermined state. So with that, I guess we're done. Tim says we're done.